Hi students, today we are going to discuss about the time-based generators. In the previous session we discussed about the exponential sweep circuit, nothing but how an exponential sweep circuit can work. At the same time we discussed about the different types of the errors in that exponential sweep circuit. So nothing but an exponential sweep circuit is designed with the combination of a resistor and a capacitor. So across a capacitor we connect a switch. From that we have to vary an output signal, nothing but based upon the capacitor charging and discharging condition, the output will be varied. So in this session we discuss about the remaining two types of the, remaining two types of the sweep circuit, that is what is meant by Miller circuit and what is meant by Bootstrap circuit. As we know that the Miller circuit, as we already discussed that, the Miller circuit is a circuit, so that is an exponential circuit. Here Miller circuit input is a step signal and output will be a ramp signal. Simply, so it is used for conversion of step signal to the ramp signal conversion. So a Miller circuit is a voltage time-based generator circuit. Here the input signal will be a step signal and output signal will be a ramp signal. At the same time, the advanced version of the Miller circuit is a Phantom circuit. Here the input signal is a step pulse signal and output signal will be a ramp signal. At the same time, a Bootstrap circuit, so Miller time-based circuit is a nothing but voltage time-based circuit and Bootstrap circuit is a current time-based circuit. Here we apply a constant current to the circuit, based upon that it produces the output. So that is about the Miller and Bootstrap time-based generator. So let us check the basic principle of the Miller and Bootstrap circuit. So what is the basic principle, how we have to modify that, and what is the circuit of the Bootstrap and Miller circuit we have to discuss. So in the first we have to take the, so that is exponentially charging circuit. So first of all we have to take the exponential charging circuit. Here the output is taken across this switch. So in the initial condition we assume that this switch will be in closed condition. So when the switch is closed, here we have to assume that the current flowing through the circuit will be I. So what happens? I is equal to V by R. The current flowing through the circuit will be I. As we know that what is the equation for I is equal to V by R. So at which condition, when the switch becomes closed, in that particular time only the current will be V by R. So but after some time we have to open this switch. What happens? When we open this switch, so actually the basic principle of this will be, so we have to flow a constant current, nothing but a constant current will be flowing across this. So when the switch is in closed condition, a constant current will be flowing across this. But when the switch is in open condition, what happens? The capacitor is nothing but, so here the current decreases. Why? Because due to this capacitance action, so the current will be decreases. So that's why we don't produce a linear output signal. So actual our aim will be a linear output signal. Why? Because a sweep circuit is an electronic circuit. Here the output is very linearly. So but from this circuit at a switch is in closed open condition, we don't produce a linear output. Why? Because the current will be changed. Nothing but current will be decreased. So this problem can be overcome by using nothing but, so this problem can be overcome by using, so maintenance of constant voltage. So for maintenance of constant voltage, so this current will be maintained as constant. For this I am connecting an imaginary voltage source, that is here the input will be, the output will be generally voltage is taken across the capacitor which is indicated with the VC. So I am adding an imaginary voltage source with different polarity. So that is here I am adding the VC with different polarity, nothing but plus and minus. Here we connect a plus and minus. So which maintains a constant current, nothing but we have to maintain a constant voltage here. So nothing but that is V is maintained as constant, R obviously constant. So then the current will be maintained as constant. So that is the simple modification in that circuit. But here I want to replace, nothing but I want to rearrange this circuit. Simply here the Z will be, the terminal Z will be connected to the ground. So here the terminal, I assume like that, the terminal Z is connected to the ground. What happens? So the Z is connected to the ground and the circuit will be look like this. And that is the input is applied in between X and Z and output is taken across this Y and Z. So let us check the condition. Here the input is applied at X and Z condition and output is taken across this Y and Z condition. So simply we have to say that what is the XZ? Generally the XZ is in between this. So that is it can be right like this. The input is we have to apply, that is VA is applied in between X and Z. So what is the terminals of the XZ? Here simply I am connecting Z to the ground, and what is the XZ becomes simply XZ is equal to XY and YZ. So which is equal to XY and YZ. XZ is equal to XY plus YZ. So that is what is the XY which is connected in positive way, that is VC, that is plus VC, and YZ nothing but it is in the reverse direction. Same voltage source we have to connect, that is a minus VC. Plus VC and minus VC which becomes 0. And what is the YZ? Here the YZ nothing but the output voltage, that is minus VC. So what is the gain of this particular condition? Or simply we have to replace this voltage. Here I am replacing this VC voltage by an amplifier. So this VC voltage and imaginary voltage can be replaced with the amplifier. So an imaginary voltage is replaced with the amplifier. At the same time, here the XZ output terminals, and that is XZ is the input terminal and YZ becomes the output terminal. From this, when the input signal is also in the 0 condition. Why? Because XZ becomes XY plus YZ. So that is plus VC and minus VC. What becomes the input signal will be obviously 0. So in the first we have to take the exponential signal, nothing but exponential circuit. In that we don't produce a constant current signal or a linear output signal at the output side. So for this we have to rectify that. How we have to rectify that? Simply I am adding an extra voltage source, that is imaginary voltage source with opposite polarities to that. So after that I am rearranging this circuit simply by connecting an extra, that is here the VC is replaced with an amplifier. So after that here the input signal, what is the VA? VA becomes 0. Why? Because I am applying the input signal in between X and Z and the input will be 0 and output will be minus VC. And what is the amplifier gain? So actually the gain of the amplifier will be infinite. Gain nothing but VI by V0. Input will be, V0 by VI. The input will be minus VC. Why? Because so we get the normal input, that is minus VC, and the output will be 0. Something by 0, that is infinite minus infinite. So that's why I am replacing this VC with an amplifier, and this is in place of amplifier I am replacing the amplifier with the Miller circuit. Why? Because Miller circuit, the basic thing is the gain of the Miller circuit will be infinite. Here the amplifier gain is also infinite. That's why I am connecting nothing but I am replacing this circuit with an Miller circuit. So this circuit will be acts as a sweep circuit. At the same time here the Z terminal is a virtual ground. Nothing but virtual ground, nothing but we assume that that signal will be a ground. So maybe it is ground or may not be ground, but we assume virtual nothing but temporary ground, like that. So or simply we have to say that so Z is equal to 0. That's why here the X is also becomes 0. Why? Because the output is taken across X. Input is applied in between X and Z. So why Z becomes 0? When Z becomes 0, the input X signal, another input signal will also be 0. So this type of input, nothing but this type of connection is known as virtual ground. So one of the terminal becomes 0, another one also becomes 0. So the another terminal, that is the first terminal which is connected to ground, is known as virtual ground. So in this time this Z terminal acts as a virtual ground. And the next one is that this is the basic principle of the Miller circuit. So simply in place of amplifier I am connecting a Miller sweep circuit. And next one is the Bootstrap bootstrap circuit. So just in the previous one I am connecting Z to ground. Here I am connecting Y to the ground. So that is what is an input signal and what is an output signal. So the input signal is just we applied at the VC level, and output is also taken across that so Z and Y terminal. What is the Z and Y terminals? Let us check the Z and Y terminals. What is the Z and Y terminals? This is Z and Y, simply plus and minus, that is plus VC. So the input is here the Y becomes ground. So then the circuit will be like this, and the input will be obviously. So the input is XZ and output Y terminal becomes ground. So that is the output is applied between X and that is VC, and output is also taken YZ. So that's why the input will be YC and output will be VC. So in this particular time the gain will be, what is the gain? V0 by Vi. So what is the V0? That is a VC. Output is also VC, that is VC, and VA becomes VC, that is VC will be cancelled, the gain will be 1. So that is the basic thing about this bootstrap circuit. Simply we have to say that in the bootstrap circuit the gain will be 1, and the Miller circuit the gain will be infinite. So that is the basic thing and basic principle of the bootstrap and Miller circuit. Based upon that we have to design a bootstrap and Miller circuit. So let us discuss about the bootstrap and Miller circuit designing. So Miller circuit. So as we know that the Miller circuit having the gain, that is gain is equal to infinite, and this is the circuit diagram of the bootstrap circuit. So simply the Miller circuit. So the coming for the circuit point of view here. So it consisting of the two transistors Q1 and Q2. The output of this Q1 is connected to the input of Q2. So at the same time this output is connected to the B. So in between these Q1 and Q2 outputs I am connecting a capacitor which is which produce that is the output will be changing. So based upon these outputs, the capacitor action will be changing. At the same time, I am applying an input signal like a pulse signal or a step signal. First, I am applying a step signal as my input signal. So what happens and what is the condition? Let us check. So at the first condition, I am applying a positive signal. That is a positive signal. So when we apply a positive signal to the transistor Q1, so what is the on condition of the transistor Q1? So that is VBE saturation 0.7 volts for silicon and 0.3 volts for germanium. So let us check, the input signal will be more than this signal, that is we apply positive signal, obviously the input signal will be more than this one. Then in this particular time transistor Q1 goes to on condition. When transistor Q1 goes to on condition, what happens? So the transistor Q1 is on condition, here the voltage becomes VCE sat. So this voltage is generally 0.3 volts. So this 0.3 volts is applied to the transistor Q2. So what happens? The transistor Q2 goes to off condition. Why? Because so the minimum voltage the minimum voltage applied to the transistor for going to the saturation region will be 0.7. But here I am applying a 0.3 volts to this particular transistor Q2. So then transistor Q2 goes to off condition. When transistor Q2 goes to off condition, that is what is the VB voltage? Generally when transistor goes to off condition, the voltage VB becomes VCC. So at that particular time, that is when a positive signal is applied to the transistor, then transistor Q1 is in on condition. When transistor Q1 is in on condition, the output will be VCE sat. So then this voltage is applied to the transistor Q2, then Q2 goes to off condition. When Q2 is in off condition, the output will be VCC at positive interval of time. So and coming for the negative going pulse, when a negative going pulse is applied to the transistor Q1, then Q1 is in off condition. So that is at positive condition Q1 is on condition and Q2 is off condition, and the output will be VCC. In that particular time it maintains a constant output VCC. After that I am giving a negative signal, that is input is a negative signal. So during this time Q1 is off condition. When Q1 is in off condition, the voltage here, the VA voltage will be VCC. So at that particular time the VA voltage will be VCC. So this VCC voltage is applied to the transistor Q2. So then Q2 is on condition. On condition. That is, during the negative interval of time, the transistor Q1 is in off condition. And when transistor Q1 is in off condition, so this VA voltage is VCC. Generally, when transistor is in off condition, the collector voltage becomes VCC. This voltage is applied to the transistor Q2. Then transistor Q2 goes to on condition. When transistor Q2 goes to on condition, the output voltage is generally VCE sat. But in the previous one it is in the VCC, now it is in the VCE sat. So it takes some time for moving of VCC to the VCE sat. Why? Because so at first condition the output is VCC, at the negative pulse the output will be VCE saturation. It takes some time for movement of VCC to the VCE sat. Why? Because there is a capacitor is connected in between these two collector terminals. So it charging and discharging, it produces charging and discharging, nothing but the capacitor. So at a particular time it may be charging, and at different time it is discharging. So at that it is connected generally between VCC and VCE sat. So due to this capacitance action, it decreases. So it does not decrease suddenly, it takes some time to decrease from VCC to VCE sat. So that is the thing about this transistor Miller circuit, time based generators. Let us check the output of this transistor Miller circuit. So that is this one is TP is so during the positive interval. So during the positive interval this will be, so the output will be VCC. So when we apply a negative interval, so it takes some time to move to the VCE sat. After that again we apply positive cycle, it takes some time to move this. So generally, so this time is known as sweep time and this time is known as return time. So that is sweep time, TS is less than compared with the TP. So this is about the input and output waveforms of the Miller circuit and operation of the Miller circuit. Very easy. So generally we take it as VC is equal to 0. So at some time, so the output will be like this also. So here we consider VC saturation and this one is out. So let us check the condition. So let us check the condition of the errors in that particular. So that is expression of the sweep speed error. So very important. That is the sweep error is very important in the every time based generator. Let us check the expression for the sweep speed error in that particular condition. So first we have to take the, so what is the basic principle of the Miller circuit? So that diagram we have to take for this finding of the sweep error. First we have to take that condition, that is expression for the sweep speed error for the Bootstrap Miller circuit. So that is the circuit will be like this. I am connecting a resistor R and the voltage source V. So in between this I am connecting a capacitor with amplifier. After that, so this output is taken at the YZ terminal and input is applied at the XZ terminal, and this one is VC and plus and minus. Here the output is taken across this. So this is taken general diagram for this. So the input will be XZ and output will be YZ. Here the Z is connected to the ground. At the same time, this circuit, now the amplifier is here. The amplifier can be replaced with its equivalent circuit, nothing but so what is the gain of the amplifier, and it can be replaced. V0 is replaced with the A into Vi. That is, as we know that V0 is equal, gain is equal to V0 by Vi, and V0 is equal to A into Vi, and I am applying a resistance at the input side, that is Ri resistance. So the amplifier can be replaced like this. And so this one will be connected to the resistance Ri, and after that, so here I am connecting a Vi, that is a V0, and this one is connected to R0, that is output impedance, and this one is YZ. Let us take it as V0. This one is YZ. And here this one is voltage V, and here there is a capacitor in between and X and Y. So just I am connecting a capacitor in between these two. I am rearrange this equation like this: positive and negative, R and Ri and R0, just capacitor. So C with the positive and negative direction. After that, if it that is transistor B. So in the transistor B, an emitter follower, nothing but here the transistor is nothing but here a transistor is an emitter follower circuit. So that is, what is an emitter follower circuit? So simply we have to say that the emitter follower circuit gain will be 1. So that is, in the emitter follower circuit, whatever the input we have to give, we get that output only. That is, Va is equal to V0. When the gain is equal to 1, obviously the output will be Va is equal to V0. So it can be, so like the resistance R0 can be replaced with the short circuit and can be replaced like this. Why? Because so that is, gain will be 1, the R0 will be replaced with the short circuit, and the circuit will be, that is the diagram will be replaced like this. Just I am short circuiting this Vi. After that, alright, and the next one is, so there is a capacitor in between these two, that is, I am connecting a capacitor here, plus and minus, that is a capacitor C. After that, it is connected to the AVI, positive and negative. V. So this is the figure C like this. So this figure can be replaced like this also. First we have to take the, what is the basic principal circuit. In that I am replacing this circuit with the amplifier equivalent circuit. Here the amplifier is just emitter follower circuit. So that is V0 is equal to Va, and I am replacing that R0 is equal to, so just R0 will be short circuited and the circuit will be like this. At this condition, that is at steady state condition, that is T is equal to infinite, the reactance of the offered by the capacitor C. What is the reactance offered by the capacitor? X is equal to 1 by 2 pi Fc, and that is as we know that F is equal to, it can be also write like this, that is T by 2 pi C. At steady state condition, that is we have to take F is equal to 0 or T is equal to infinite. At T is equal to infinite condition, what is the Xc? Xc is equal to infinite. When Xc is equal to infinite, what is the condition of the capacitor? Capacitor can be replaced with the open switch. So that is when the reactance of the capacitor becomes when t is equal to infinite, during that time the reactance of the capacitor also replaced with reactance will be infinite. That's why it can be replaced with the open switch. So just I have to redraw this circuit. Just I am representing with the P and Q. So this is V Thevenin. So just I have to replace this capacitor with the open switch and take P and Q values that can be replaced with the V Thevenin. As we know that what is meant by V Thevenin, which is VI. VI nothing but, what is the VI? I into R. That is where is R? What is the R? R is equal to Ri. We have to take R is equal to Ri. So V Thevenin, which is equal to taken across the resistor Ri, that is I into Ri, and what is the that is Vi, which is equal to I into Ri. That is so where I, what is the I? Where it starts here, that is V by R plus Ri. V by R plus Ri. So just V Thevenin is equal to V by R plus Ri into Ri. And what is the R Thevenin? So these two are connected in parallel. That is R is in parallel with the Ri. So that is R into Ri by R plus Ri. That is R into Ri by R plus Ri. So this is the V Thevenin and R Thevenin of this particular circuit. So this circuit can be also, that is this circuit can also be replaced like this. That is with R Thevenin. In place of R and Ri, I am replacing that with R Thevenin. R Thevenin and capacitor plus and minus, and this one will be VC. After that, the input is V Thevenin, and the next one is, so just this circuit. In place of here, I am replacing this VI. R into Ri is replaced with the R Thevenin. Here the VI, and next current is replaced with the V Thevenin, and as usual AVI and V naught. What is the V naught? Where we have to take the V naught? So that is V naught is equal to A into Vi. So that is we have to replace like this. V naught is equal to A into Vi, and Vi nothing but V Thevenin, A into V Thevenin, and that can be replaced like this, or that can be represented like this. What is meant by V Thevenin? V Thevenin is equal to Vri by R plus Ri. That is a sweep error. What is the equation for the sweep error? That is maximum sweep amplitude by, so maximum output. So sweep error is equal to maximum sweep amplitude by maximum output at t is equal to infinite condition. So in that particular time we have to represent years. What is the maximum sweep amplitude? What is the, it can be represented with the Vs, and maximum output at t is equal to infinite. What is the maximum output we get? That is V naught A into Vri by R plus Ri. In that particular time we have to write like this also, Vs into R plus Ri by A V Ri. So just take Vs by Av as common. Just take Av into Vs by Av in the side. So then it can be write like this: R plus Ri by Ri. After that, so what is the condition? Just Ri will be cancelled and it can be write like this also. So that is 1 plus. So that is it can be write like this: Vs by Av into Ri and that is 1 plus R by Ri. And what is that? It can be represent like this. That is Vs by Av into 1 plus R by Ri. That is a sweep error. And next we have to discuss about the transmission error. The transmission error, as we know that the transmission error is Et is equal to Es by 2. So we know the sweep error nothing but so we get that Vs by Av into 1 plus R by Ri, and transmission error which is the difference between input minus output by input. So it can be represent like this: Es by 2. So just Vs 2Av 1 plus R by Ri. So that is a transmission error. And next we have to discuss about the displacement error. So what is the displacement error? Displacement error is the maximum deviation by sweep amplitude. That is Es by 8. Vs by 8 Av 1 plus R by Ri. So these are the different types of errors which are presented in the Miller sweep circuit. So this is about the Miller circuit and what are the different types of the errors present in the Miller sweep circuit. And next we discuss about the bootstrap circuit and what is meant by bootstrap circuit. So in the Miller sweep circuit we have to go for the infinite gain. So the gain of the amplifier will be infinite, but here the gain of the amplifier will be generally 1. That is it consisting of unity gain. So here coming for the circuit designing point of view, so the transistor Q1 output is connected to the transistor Q2 as usually, but so here the output is taken at the emitter terminal of the Q2. So for bootstrap and Miller circuit, so already you have to study in the BD subject. So what is the amplifier? We have to know what is the bootstrap principle and what is the Miller operation. So simply in the bootstrap the output is taken at the emitter terminal of the transistor Q2. So in that particular time, as like that, we apply input signal. So like a pulse signal, first I am applying this signal. So when a positive pulse is applied to the transistor Q1, so when a positive pulse is applied to the transistor Q1, what happens? Q1 is in on condition. When the Q1 is in on condition, so that is generally what is an input voltage for transistor Q1 goes to on condition, that is VBE saturation for 0.7 for silicon and 0.3 volts for germanium. This voltage is given to that so transistor Q2, but actually when transistor Q1 is in on condition, what is the VA? VA becomes VCE saturation. So in that particular time the VA becomes VCE saturation. So this is applied to the transistor Q2. So that is VA also be write like this, that is VBE of Q2 and V0. So why? Because this VA voltage is splitted here, that is VBE of Q2 and V0. Just I am representing like this also. VA is equal to VBE of Q2 plus V. Actually, so in that particular time, what is the VA? VA is equal to 0.3 volts. And what is the VBE? Q2. So when transistor Q2 or Q1 anything becomes on condition, it becomes 0.7 volts. So that is 0.7 volts plus V0. As we indicate that V0 is equal to 0.3 minus 0.7, that is minus 0.4 volts. So this is at V0 condition, we have to take the output at V0. So this voltage is given to the diode. So this voltage is applied to the diode too. So through a capacitor CB. So in this particular time the transistor are, so this can be indicated with the VCC and this can be indicated with that so minus a negative signal. So the negative signal is applied to the cathode of the diode and positive signal is applied to the anode of the diode. So that diode becomes, in that particular time D becomes on condition. So when the diode is in on condition, here the VB voltage. So what is the VB voltage? When it can be replaced with the short switch. So this VCC signal is flowing here. That is VB becomes VCC. So this in that particular time the output will be like this. That is when we apply a positive signal to this condition, then Q1 is an on condition. So this VA voltage is applied to the transistor Q2 plus V0 generally. So that is so we have to indicate like this. So VA is equal to VB of Q2 plus V0. From that, what is the V0? V0 is equal to 0.3 and 0.7. From that, we have to get the V0. So this V0 is applied to the diode cathode terminal and anode terminal is connected to the VCC. So then diode D becomes on condition. When diode is on condition, this VCC voltage is applied to the VB. So in that particular time, so this the output VB is VCC. And when we apply a negative voltage signal to this, so when we apply a negative voltage to this transistor Q1, so what is that? So when transistor Q1 is in off condition, obviously this VA voltage will be increases. So when this VA voltage increases, as we know that the VA becomes so VB sat plus V0. When the VA voltage increases, obviously the potential at B will be increases. Why? Because just check the condition. VA is equal to VB of Q2 plus V0. From that V0 is equal to VA minus VB of Q2. So this is constant, that is 0.7 volts. So when this VA voltage is increases, obviously this V0 will be increases. So maybe it is up to VCC also. So this is given to that diode cathode terminal. So in that particular condition, what happens? So when a negative signal is applied to the transistor Q1, in that particular time this VA voltage will be increases. So gradually this increases voltage also causes to increases the V0. So this is applied to the cathode terminal of the diode. So during this time diode is off condition. Simply we have to indicate that the VB voltage also increases. Why? Because so obviously this VCC voltage is coming to here. That is VB is indicated like this. VB is equal to, so that is VCC plus VA. Why? Because just VB saturation is minimum voltage. So we have to neglect that when VA is more than, so when VA is far greater than VB sat, in that particular condition just I have to neglect that VB sat. So that's why V0 is equal to VA. That's why VB is equal to VCC plus VA. So from that figure we have to indicate that here the major thing is a constant current is flowing to that circuit. That is I is equal to, what is the I? Where it starts? It starts at the position of VB and ends at the position of VA. VB minus VA by RC 1. After that, so what is the VA? As we know that here the VA becomes, what is the VA here? So that is VA becomes, what is the VB? As we know that the VB is equal to VCC plus VA. That is I is equal to VCC plus VA minus VA by RC 1. VA cancelled. The current will be I is equal to VCC by RC 1. So this current I is splitted here. So this I current will be, so generally split here, that is IC1 and I1. So that is I is equal to IC1 plus plus I1. So in that particular time, that is here I am applying a negative signal to the transistor Q1. In that particular time, what is the condition of Q1? Q1 is an off condition. When the Q1 is an off condition, obviously IC1 current will be 0. So simply we have to say that the I is equal to I1. So this I1 current is splitted here like this, that is I2 and I3. That is I1 is equal to I2 and I3. So from we have to say that here the I3 current is current flowing through the transistor Q2 base terminal. At the same time, so here that is here the transistor Q2 is an emitter follower circuit. So what is the emitter follower circuit? Emitter follower circuit having high gain, that is a high input resistance. So that's why when high input resistance will be there, so then obviously the I3 current will be, so that is V is equal to IR and I is equal to V by R. So there is the resistance will be more. What happens? That is let us check assume like that the resistance will be infinite. Then I becomes 0. So in that particular condition I3 will be 0. Why? Because here I am using an emitter follower circuit. For emitter follower circuit the input resistance will be more. For that I3 will be 0. So that's why I am representing like this. The I3 is equal to 0. Why? Because the emitter follower circuit which is having the highest input resistance, that is I1 is equal to I2 at that particular time. So here the I2 will be constant. So now, so this is our major thing will be a constant current is flowing through this circuit, then the output will be like this. At the same time we have to check the output condition, and what is an output? Let us check the condition. So first we apply, this is an operation. So for coming for the operation, a constant current is flowing to this circuit. Across this circuit it produces an output signal. So first we have to test the condition, and what is a V0 condition. So just this is an operation of the circuit, but our major target is what is the V0. So at the first condition we apply a positive signal to that the Q1. So in that particular condition Q1 is an on condition. So when Q1 is an on condition, this is VC sat, and V0 becomes VA minus, that is VA and minus of VB sat. Simply this voltage will be minus 0.4 volts. So in that particular time the voltage will be 0.4 volts, and when negative signal is applied to the transistor Q1, then VA becomes VCC. So this is like we have to say that VA plus VB sat is equal to VA minus VB sat is equal to V0. So and here just VA where VCC minus 0.7 volts simply. So it is nearer to the VCC. That's why V0 is equal to VCC in that particular condition. So just check the output waveforms of this particular condition. So that is here I am indicating with 0.3 volts, or the correct output will be 0.4 volts when a positive signal is applied to this, that is 0.4 volts. After that we apply a negative signal to this. In that particular time the output will be VCC. So that is the output is transition between these 0.4 volts, that is negative voltage and positive voltage. So this is an operation of the Bootstrap circuit. So let us check the difference between Bootstrap and Miller circuit. So that is as the circuit implies a positive feedback. So in the Bootstrap circuit we have to use the positive feedback here. So and coming for the Miller circuit we use a negative feedback. And coming for the output waveform, so we observe that in the Miller circuit, Bootstrap circuit, the output is a positive going ramp, nothing but positive going ramp, nothing but it starts with a negative level and increases positive. So that we have to consider a first condition, that is the output is positive going ramp signal. This one. And for Miller circuit, the output is negative going ramp. So let us check the output of Miller circuit. So this is a negative going ramp. At the starting condition, the output is a negative going ramp. But in Bootstrap circuit, the output is positive going ramp. And another thing is the circuit employs emitter follower. So in the bootstrap circuit we have to use the emitter follower. The gain of this bootstrap circuit is unity. At the same time, so here also the circuit requires amplifier. So in the Miller circuit we use an amplifier circuit which is having the gain, so that is infinite. So these three are the major important things. And the final one is the amplifier having high input resistance. At the same time, amplifier with the high input resistance is not necessary. So in the bootstrap circuit, obviously amplifier with high resistance will be used. Why? Because we have to maintain a constant current. That is I is equal to maintain as constant in the circuit. So that's why we have to maintain a constant, that is we have to maintain a high input resistance here. But here we need not to use that condition. So this is about the difference between Miller and bootstrap circuit. So again we have to find that what is an expression for the sweep speed error in that particular bootstrap circuit. So let us take the circuit diagram of that bootstrap circuit, nothing but circuit diagram, nothing but. So we have to find that is what is the, so principal diagram, like so this one is Vi, sorry, that is V, and resistor R. After that, here that is capacitor Vc, and it is connected to the amplifier. V0. So the output is taken in between Z and Y, and input is applied in between X and Y. So here, so just take that here the amplifier circuit is also replaced with the, so it's equivalent circuit like this AVI and RI. So just like that I have to represent like this. So and here Ri, and the next one will be A into Vi. After that it is connected to R0, and this one will be V0, Zy, and this one is Xy with capacitor C. So here, so let us check the condition. Here the transistor is emitter follower circuit. So for the emitter follower circuit, the gain of the amplifier will be 1, and this R0 can be replaced with a short switch. So just I have to redraw this circuit with replacing by R0. So like this. So why? Because the R0 will be short circuit, and here I am using, so emitter follower circuit, that is A is equal to infinite. So the resistor so can be replaced with a short switch. That's why the circuit will be like this. So at the steady state condition, so the sweep speed error is find out at the steady state condition, that is T is equal to infinite condition. So like that, at steady state condition we have to, so the reactance offered by that, so that is the reactance offered by the capacitor is infinite, as already we have to find that. So at steady state condition the reactance offered by the capacitor is infinite. So that's why the capacitor is replaced with the open switch. So that's why we have to eliminate this capacitor, or we have to just eliminate this capacitor, and the circuit will be like this. R, just it can be written like this also. Here I am applying V input. Why? Because so the reactance at T is equal to infinite condition, the reactance of the capacitor will be infinite. So when that particular condition, the capacitor can be replaced with the short switch, sorry, open switch. That's why I am applying here like this. That is Ri, and sorry, this one is X and Y. We have to apply inputs. So here the figure D can be redrawn like this, like this. That is, so this figure can be redrawn. So that is, in between this there is X. I am indicating that X. After that, so this is AVI and this one is AVI is in between Y and Z. So that's why I have to connect like this, which is connected to ground. That is I. So from that, what is the V naught? As we know that V naught is equal to A into VI. And what is that? VI is equal to, what is the VI? I into RI. And from that, by applying KVL to this circuit, what happens and what is an output here? That is V. V minus I into R minus I into RI plus AVI, that is which is equal to 0. And from that we have to find that, so just check the condition. V minus, take minus I, that is R plus RI, and plus AVI nothing but V naught, which is equal to 0. From that I have to find the current I. Why? Because in the constant current sweep nothing but in the bootstrap circuit we have to find the current only. So like that is, so we have to indicate like this, I into R plus RI is equal to V plus V naught. And what is an I? From that I have to find the current I. I is equal to V plus V naught by R plus RI. So that is a condition. So this is taken as equation number 2. So what is an equation number 1? That is VI is equal to I into R. So just substitute this equation number 2 in equation number 1, and what happens, that is VI is equal to I into RI. So that is VI is equal to V plus V naught by R plus RI into, what is the condition? That is RI. Sorry. V naught is equal to A into I RI. In that I have to substitute that in place of I. A into I nothing but V plus V naught R plus RI into R. So after that, what is the V naught? We have to find like this. That is V naught is equal to R plus RI A into, we have to indicate the V naught. V naught is equal to R plus RI, which is equal to, so that is A into RI of V plus A into RI of V naught. So just we have to write like this. So from the previous equation we have to write this equation. So just take V naught as common from this equation. Just take V naught terms in the one side. That is V naught of R plus RI minus of A into RI V naught, which is equal to A into RI of V. So just take V naught as common. That is R plus RI minus of ARI, which is equal to A into RI of V. So from that we have to find the V naught. V naught is equal to A into RI of V by R plus RI by minus A into R. So as we know that what is an equation for the sweep speed error? The sweep speed error is equal to maximum amplitude by, so at maximum amplitude by maximum output at t is equal to infinite. So at t is equal to infinite condition we get this output. So that is Es is equal to maximum amplitude will be Vs by A into Ri of V by R plus Ri minus A into Ri, and here So Vs by Av, let us take this Vs by Av as common. It becomes R plus Ri minus A into Ri by Ri. So then, what is the Es? Vs by Av, and it becomes, just take that Ri, R plus Ri. So just take Ri as common in this both two terms, that is 1 minus A. And after that, I have to write like this: Es is equal to Vs by Av 1 minus A plus R by Ri. Just Ri cancel here. So that is R plus R by Ri into 1 minus A. So that is the speed error. And coming for the transmission error, as we know that the transmission error is Et is equal to Es by 2. What is an Es? That is a Vs into 2Av 1 minus A plus R by Ri, and Ed is equal to Es by 8. Vs by 8 Av 1 minus A plus R by R. So this is the errors of the bootstrap circuit. So this is about this today's class. So in this class we discuss about what is the Miller circuit and what is the bootstrap circuit. At the same time, what is the basic principle of bootstrap and Miller circuit, and what is the difference between these two circuits, and what is the finding of sweep error, transmission error, and displacement errors of this. So bootstrap and Miller circuit. So in the, this is fifth unit, that is the sweep circuit. So in the next class we will discuss about the unit 6, that is logic families and sampling gates. Thank you.